Welcome to Math 31 as we are into Chapter 8, looking at derivatives of exponential and logarithmic functions. In 8.2, the section we'll be looking at today, we will be looking at derivatives of exponential functions. And in particular, we'll be looking at the derivative of e to the x, as you see here in question 2. So e is Euler's constant. So as you look at your calculator, you'll probably see a button that looks like ln. It might look like in. It's a lowercase l. ln, this is a natural logarithm. So if ln of x, this is the same as the log base e of x. And possibly as the function or a second function on your calculator, you'll have e to the x as an option. So if you enter e to the exponent 1 on your calculator, you'll find an approximate value for this constant. And it is approximately 2.71828. If you look at your screen, it may look like it starts repeating, but it actually doesn't. It's an irrational number, kind of like pi, and it's a very special number in mathematics. In particular, it has special use when it comes to exponential and logarithmic functions. So kind of like pi is to circles in geometry, e is to exponential and logarithmic functions. So we're going to be making use of Euler's constant today as we work through quite a few of our questions. And here you see in question number 1, we are asked to find what is the limit as h approaches 0 of e to the h minus 1 all over h. And I'd like you to do this using a table of values. I probably should have called this a warm-up question. So why don't you get out your calculator, do a table of values, and if your graphing calculator is handy, or Desmos if you're working at home, you can actually plug this in, replace the x's, or I should say the h's with x, and look at the function and see as h approaches 0, what does this rational expression approach? You can pause the video now to figure out the value. Well, here's my table of values. And I can see as I approach 0 from the left, so as we come from the left, my values of this rational expression looks like it's approaching 1.995. And as I approach from the right, similarly, it's decreasing, but it looks like it's approaching 1. So it looks like the value of this limit will equal 1. So let me just write that up here, the limit, not lomit, but limit as h approaches 0 of e to the h minus 1 over h is equal to 1. Now that'll be useful to us in a moment. But first, let's look at this graphically just to see that we're getting the same result. So as I pull this over here, this is the graph of this expression if I had y equals e to the x minus 1 all over x, so this rational expression. And I can see from the left I'm approaching 1, from the right I'm also approaching a y value of 1. Well, we want to use the definition of the derivative to figure out what's the derivative of e to the x. So you will remember the definition of the derivative would be the limit as h approaches 0 of, this would be my f of x plus h minus f of x all over h. Well, in order to evaluate this limit, notice here I'm adding exponents. When do we add exponents? It's when we were multiplying powers of the same base. So I'm going to rewrite that e to the x plus h as e to the x times e to the h. So I'm separating it into two separate exponential expressions. Then you'll notice I have an e to the x here and e to the x there. And that e to the exponent x is a common factor that I can pull out in front in my numerator, and then I have an e to the h minus 1. And now you are probably seeing why we did that first question. Well, before I look at this e to the h minus 1 part, this e to the x, it doesn't have an h. So I can actually factor that out in front of my entire limit because it doesn't depend on h. As h goes to 0, e to the x doesn't change. And so here I have the limit as h approaches 0 of e to the h minus 1 all over h. And we just discovered that this whole limit is equal to 1. So what I've discovered, or what we've discovered using the definition of the derivative, is the derivative of e to the x is e to the x. Mind blown. What does this mean? It means for this graph, if I was to graph y equals e to the x, the slope at any point would equal the y value at that point. Well, let's look at Desmos here. So here, can't see it, but this is the graph of y equals e to the x. And what I'm going to do, I'll just change the size here so you can see what I'm graphing. Desmos lets me plug in y equals f prime of x. So if f of x is e to the x, y equal f prime of x will be the graph of the derivative. So when I turn on this graph of the derivative, it overlaps exactly. In other words, at any point here, so when x is 1.194, the y value is 3.3, that also means that the slope of the graph at this point is 3.3. Well, this may become your favorite derivative of all the derivatives we've done so far. Let's look at a few examples where we will apply our understanding of all the different rules, but now introducing this derivative that we have here. So, question number 3. What I have is a composition of functions, because in my exponent, I have a function of x. So let me just write beside here that I'm going to be looking at the graph of, or not the graph, but the derivative of e to the g of x. What's going to happen? Well, the chain rule says I take the derivative of my outside function. So y prime, the coefficient of 2 stays as it is. Derivative of e to the something is e to the something. But then we need to multiply by the derivative of the inside function. The inside function was this 3x. So it'll be times 3. So simplifying this derivative a little bit, I'll get 6e to the 3x is the derivative of this function. So looking back here and thinking about the chain rule would say y prime would be this function, the derivative of this e to the something is e to the something, the inside stays unchanged, times the derivative of that inside function. So this is what the chain rule will look like for this exponential function e to the exponent g of x. Let's look at number 4. This time I have a product of functions. So I have x times this e to the g of x. So again, there's going to be a chain rule in there. So I'll start writing down here y prime. Product rule says I keep the first function as it is, times the derivative of the second function. Well, derivative of e to the something is e to the something, times the derivative of that something, which is a 2x. I'll put it in brackets here. Plus my second function, which is e to the x squared, times the derivative of the first function, derivative of x, is just 1. So there's the derivative. Now what we'll find is for simplifying these derivatives, quite often we will have a common factor. And you can see here that this e to the x squared, e to the x squared is common to both of these. So y prime will equal e to the x squared, and then the leftovers, the x times 2x is a 2x squared, and then plus a 1. And there's the derivative for question number 4. Let's look at number 5. For question number 5, I need to think about a chain rule again, and actually a couple layers. So this is like an f of g of h of x. So my outside function is the sine function. And then one layer in, I have this 2e to the something. And then my innermost function is that negative x that's in the exponent. So let's do this derivative. Outside function. So y prime, derivative of sine of something, is cosine, and we keep the inside unchanged. So still 2e to the negative x times the derivative of this inside. Well, the coefficient of 2 will stay, and derivative of e to the something is e to the something, times the derivative of that something, which is a negative 1. And if I want to simplify this a little bit, typically we would take these terms out in front of the trig function. So I'll have a negative 2 e to the negative x times cosine 2e to the negative x. Question number 6. Again, we have a few layers to a chain rule. We've done so many derivatives with square roots that I'm not going to rewrite it with an exponent of a half, but I'm going to think of it as though it had that exponent. So my derivative, outermost function, I'll bring down the half. The inside will be unchanged, and then I'll subtract 1 from the exponent. Then I'll look at this inside function. Again, it's unchanged in here, 1 plus e to the negative x, and then times the derivative of this inside function. Derivative of 1 is 0. Derivative of e to the negative x will be e to the negative x times derivative of negative x, which is negative 1. And again, if I was to rewrite this, this 2 will be in the denominator. Actually, this negative exponent of x, I could also take to the denominator. So I think I'll even do that. So I'm going to have a 2 and e to the positive x. Remember, when we have a negative exponent like this, I can take that power into the denominator and give it a positive exponent. And then we have the square root of 1 plus e to the negative x. And this one I'll just leave as an e to the negative x. And there we have our answer for question number 6. Number 7. Here we're going to need a quotient rule. So let's think through the quotient rule. My derivative will be low d high. So my denominator, maybe I'll do my denominator in black. So denominator e to the negative x plus e to the positive x. D high, derivative of e to the something, is e to the something times the derivative of that something. Minus high, e to the 2x. D low, derivative of e to the negative x is e to the negative x times negative 1. So I'll just put that negative in front. We've done a number of those already. Plus derivative of e to the x is e to the x. All over the denominator squared. And there we have our unsimplified derivative. If we move on to simplifying, notice these two black brackets in the numerator are not quite exactly the same because here I have a negative coefficient in front of this e to the negative x. There it's positive. So it's not a common factor that I can take out. But there is that e to the 2x that we could factor out. So let's factor out that e to the 2x. And then I have this 2 left over that I'll distribute into this first black bracket. So that'll give me a 2e to the negative x plus 2e to the x. And then I'm subtracting the second black bracket. So subtracting the negative turns it into addition. So plus e to the negative x, and then minus e to the positive x. And then we'll collect like terms in the numerator. And there's a simplified derivative. Now, are there different ways we could write this? Sure. But we'll just stop at this point. With logarithmic expressions and exponential expressions, there's often multiple ways that we can rewrite a single expression. Let's go on to question number 8. And here we'll need to look at implicit differentiation. So on the left, when I take the derivative, I'll have e to the xy, so that stays unchanged, times the derivative of that exponent, which will be a product rule. First times the derivative of the second, plus the second times the derivative of the first is 1. And this equals dy dx. And then we want to go through and isolate the dy dx. So I begin by distributing that e to the xy into that bracket, and then I subtracted the dy dx over to the left side of the equation. And then I'll have the two terms, xe to the xy with the dy dx minus 1 with this dy dx. So right away I'm going to pull out that common factor of dy dx. And this middle term that didn't have a dy dx, I'm going to subtract it to the other side of the equation. And then we can divide out that bracket to isolate the derivative of y with respect to x. And there we go. The next page, I think, will get us into some check your understanding questions. So why don't you pause the video at this point. Let's see what we have. All check your understanding on this page, and then we'll have another example on the next page. So pause the video here, restart once you've finished the questions on this page. Here's my derivative for number 9. E to the something, derivative is e to the something times the derivative of the something. So derivative of cos is negative sine x. And then I just brought that negative sine x out in front. Question number 10. Very similar to the one we did before, a product rule. First function times the derivative of e to the negative x plus the e to the negative x times the derivative of x. And then again, I factored out that common factor of e to the negative x. Next one, my outermost function is a square root. So I'll bring the half down in front. So we'll see multiple steps here. Bring the half down in front. And then we'll subtract 1 from the exponent. So we have that negative half. Inside function stays unchanged. Times the derivative of the inside, derivative of x is 1. Derivative of e to this g of x function is e to the g of x times the g prime of x. So this is the derivative of 1 minus x squared. So that's where it comes from. And notice it only multiplies this e to the 1 minus x squared. It doesn't multiply to this 1. So it's inside these brackets here. And that's it for that question. Number 12. Again, we have a product rule. So here's my process. First function times the derivative of sine 2x plus the sine 2x times the derivative of the first function. And then again, I pulled out that common factor of e to the 3x. Question number 13. A little more involved than the example that we did earlier. So I start with the y times the derivative of e to the x is just e to the x, plus my second function, which is e to the x that I didn't actually write in. Let me fix this. All right, this is looking better. So again, as I look at this left-hand side, I have the first function times the derivative of e to the x plus my e to the x times the derivative of y with respect to x. And then on the right-hand side, bring down the 3, subtract 1, keep the inside unchanged, times the derivative of y with respect to x. Well, then I'll collect the dy dx terms onto the left, and this y e to the x I'll subtract over to the right, pull out that common factor of dy dx, and divide the leftovers onto the right-hand side. There, I hope that works out now. Let's move on to our next example. So another question similar to what we did way back in chapter 2, where we want to find the determine where we have a horizontal tangent line. But this time we have this exponential function with e to the exponent negative x here. So if we want to find the horizontal tangent line, we start by finding the derivative. So first function times the derivative of the second plus second times derivative of the first. So product rule again. We'll set our derivative equal to 0 and factor what we have on the right-hand side. So I was able to factor out an e to the negative x, but then also there was a common factor of x that I could take out. So with these three factors, I come up with three possible solutions, except e to the negative x can never equal 0. So if you remember any exponential function, e Euler's constant is about 2.18 something. And for exponential functions, typically their graphs will have a shape where if our b value, in this case the e, is greater than 1, our graph is going to curve up like this. So it has a horizontal asymptote where y equals 0, so the function can never equal 0. What does that negative do? Well, the negative changes the x's, so it's a reflection in the y-axis. So the graph actually is going to curve down like this, but still it will have this horizontal asymptote along the x-axis. So there are no values for x that can make that equation true. And then we have our next factor, x could equal 0, and our final factor, 2 minus x could equal 0, which gives us x could be 2. So we get 2 points where the function will have a horizontal tangent line. At 0, 0, notice I found the y-coordinate as well. If I plug a 0 in for x, this e to the 0 will be 1, and e base to an exponent 0 is 1, times this 0 in front. And then if I plug in 2 for x, I'll get 4e to the negative 2. So there we have two ordered pairs where that function will have a horizontal tangent line. Well, nothing really new, but here we go. You have a chance to practice another question. So try this question. When you finish, restart the video and compare your answer with mine. So you can pause the video at this point. Here you go, a quotient rule, low D high. The D high, there we needed to use that chain rule again. Minus high D low, square the bottom, there you go. Plug in the 4, evaluate, and it turns out that we get it equal to 0. Why is that happening? Well, let's look here. Here, this 2 times the square root of 4 will be a 4. So this 4 and that 4 cancel out, leaving me with e squared minus e squared. My numerator goes to 0. So it turns out that at this point, my function has a horizontal tangent line. If my slope is 0, then I just have y equals a constant e squared over 4. And we will typically leave our answers with the e in it as exact values, and that's what we were asked to do in this question, use exact values rather than getting a decimal approximation. There you go. Derivative of e to the x is e to the x. In our next lesson, we'll look at derivatives of other exponential functions, but we'll also get into logarithmic functions too.